So we've talked about reaction rate, rate laws, and integrated rate laws. We're going to get more specific now and talk about mechanisms within the concept of collision theory. So the big idea here is like, why is rate law data important? Why is the rate law such a big deal? So, if we have a reaction A to products, and we determine that the rate law is rate equals K times the concentration of A squared, why is this such a big deal? Why is this so important? Well, the reason why it's important is because it allows us to determine exactly how this process occurs. Because most reactions are not one step. Most reactions are actually multi-steps. Even though it appears overall that A is being turned into a product, A might be getting turned into something else first, and then that something else is turning into something else, and that something else is turning into a product. Through rate laws and through data of reaction rates, we can determine the exact steps for this overall reaction to occur. But in all cases, collision theory dominates. So just a quick refresher about collision theory. For any reaction to happen, what must be true? Molecules need to have the correct orientation. They have to be facing the correct direction. They have to face each other in a particular way. And number two, they must have enough energy for a reaction to occur. There's a name for that energy. It's called the activation energy, E sub A. And we're going to get into a little more specific detail right now about what that actually means. But first, let's use an actual example to guide our reasoning. So what you're looking at here is a reaction that we're going to do a lab on in class. We're going to try to figure out the rate law of this reaction with our own data. The reaction is we take this compound that's called crystal violet. So just to be clear, C and V are not elements on the periodic table. This is not carbon and vanadium. This is crystal violet. And it's a dye. It's a purplish dye color. When you react it with NaOH, with a base, it forms the hydroxide, the protonated form of crystal violet. And over time, so from 0 to 90, 180 seconds, this is in seconds here, that purple color disappears. And as you can see, it becomes colorless. What we're going to do is, in our experiment, is we're going to figure out how to measure how fast that's happening. But we do know a few things about this reaction. So let's say first, okay, that we have this energy diagram here. Why is this energy diagram important? Well, it tells us the energy of the reactants and the products and a lot of other things. So for example, on the left side, this is the energy right here, the potential energy of our reactants. So this is the energy of CV and OH, okay, as separate compounds. In order for this reaction to occur, we said that some energy needs to be added. They need to have enough energy. That's what we can see here, because as the reaction progresses to the right, the amount of energy in the reaction is increasing until we get to a certain point. Once we get to that certain point, we've added enough energy. And this height right here, not all the way to the bottom, the height from the initial to the highest point, this is called the activation energy. The energy for this reaction to start. So for this reaction, it's 60 kilojoules. This reaction needs 60 kilojoules of energy to start. Then, at this top point, we don't have CV and OH separate anymore. We have something that's in the middle. We haven't made our products, but we don't have our reactants. We would have something that's, I'm going to draw with like a dotted line. CVOH, something like this. This molecule is in between. This is called the transition state. It's called the transition state because we're transitioning between reactants and products. We don't have reactants, we don't have products, we have some molecule that's kind of in between. Eventually, we're going to get to this bond is going to form, the potential energy is going to drop, and we're going to have our CVOH, our products, are being formed. As we can see in this diagram, the energy, we started with 40 and we ended with 20. So the change in energy, the change in enthalpy, is final minus initial, 20 minus 40, negative 20. So this is an exothermic reaction. If we had an energy diagram that looked like this would be endothermic, because the reaction now has more energy than it did initially. The other thing we need to know about energy diagrams, what's actually happening with the molecules conceptually? Reactants, bonds break. We had to break some bonds between CV and OH. Then, when we make products, bonds form. Bonds are made. New bonds are made. And depending on the energy of the bonds being formed and made, that tells us if the reaction is endothermic or exothermic. Main concept to walk away from is you need to know how to interpret these diagrams. Tell me if they're endo or exothermic. You need to figure out how to calculate the energy, activation energy, and understand this concept of reactant bonds breaking, product bonds forming. There's a few other vocabulary terms we need to know. When a reaction occurs, we need to be able to figure out the molecularity of that reaction. So for example, if we have the reaction O3 turning into O2 plus O, there's only one molecule that's a reactant, O3. So we would say this is a unimolecular reaction. Need to know that vocabulary word. So if you just have one reactant, it's unimolecular. That makes sense. What if we have two molecules reacting? So if you have NO plus O3 forming NO2 plus O2. I now have one molecule here, one molecule here. So this is called a bimolecular reaction. And last but not least, if I had a reaction like this, 2NO plus O2 producing 2NO2, okay? Two molecules plus one, three molecules involved. This is called a ter-molecular reaction, not ter. One molecule reactions are most likely to happen, unimolecular, because you just need one molecule to collide and break down and have enough energy. With two molecules, you need two molecules to face each other in the right orientation. That's a little tougher. And for a ter-molecular reaction, you need three molecules to all orient and face each other in the right way and have enough energy. So these are kind of like the least likely, and these are the most likely to occur. However, most all of these reactions don't occur in one step. A lot of them occur in multiple steps. So for example, let's say this word mechanism basically means the steps. Okay? If we are, like I said from the rate laws, we can figure out the steps that are involved in a reaction. So let's say we know that a reaction happens in two steps. Here's step one and here's step two. Molecule A gets turned into Q. That happens very quickly. Then Q reacts with molecule B to form C plus D, and that's a slow step. There's a few things we need to know about mechanisms. Number one, if you're given the steps, how do you get the overall reaction? That's the first thing. So to get the overall, you add the steps. So it's just kind of like equations. Add these steps together. So rewrite everything on each side of the arrow. So on my reaction side, I have A, Q, and B. So it's A plus Q plus B. Now on my product side, I have Q plus C plus D. Now it's kind of like when we were doing net ionic equations. Does anything cancel? Do we have anything on both sides? The Q's do. So what we're left with is A plus B forms C plus D. So this would be the overall reaction. So you need to know if you're given the steps, how do we figure out the overall? Another vocab term you need to know is the word for Q. Q is a special molecule. Okay? Q is special because it's not a reactant and it's not a product. We don't see Q in the overall reaction. However, it is involved. It's in between. And since it's in between, it's called an intermediate. So molecules that are intermediates are molecules that show up in the mechanism, so in the steps, but not in the overall process. The last bit of vocabulary we need to know is the name for the step that's the slowest. The slowest step is called the rate-determining step. Determining step. Often also called the rate-limiting step, and abbreviated as like the RDS or the RLS. What's special about the rate-determining step? Well, it allows us to figure out a lot of things involved with the rate law and the kinetics. But this step is going to be very important because what we will know, what we need to know, is the rate law of the overall reaction, so of this, will equal the rate law of the rate-determining step. That is the one thing, big thing to walk away with about the rate-determining step. The rate law of the rate-determining step is equal to the rate law of the overall reaction. And we'll get a lot of practice in class with how that actually works. But conceptually, what does this rate-determining step actually mean? Well, let's say that you're driving a car, okay, here's a car, and there's 2 toll plazas that you have to go through, okay? Boom, until you can get to the other side. Let's say there's, a gate at each. Here's my gate, okay? And the gate at the second one is broken. So you'll be able to fly through the first one, no problem. But when you get to the second one, it's not working normally. It's broken. It's going really slowly. So it's going to take you a lot longer to go towards through the second one than the first. So here, the rate-determining step, the thing that's preventing you from going from one side to the other, or the thing that's affecting your speed the most, is the second gate. So this is like the rate-determining step. If we want to go from side of the bridge, reactant side of the bridge to the product side, the first step doesn't matter at all because this gate's working totally normally. It's a very fast step. This one's not working, so this is the second step, the rate-determining step, is going to prevent us from turning into product. So in this reaction, the first step, this occurs very quickly. It has no effect on the rate. The second step is the rate-determining step. It's slow. It's like the second gate and is going to affect our rate, which means the rate law will be equal to the rate law of the overall reaction. Last thing, a lot of content here. What if we have a 2-step energy diagram? If we have this reaction and we drew its energy diagram, we need to draw 2 curves. Since there's 2 reactions happening, we have 2 activation energies. So here we have the energy of the reactants. Some energy must be added. Boom, we hit our first transition state. We get to our intermediate. This is Q. Q is our intermediate. It got formed in between. Then Q reacts, again, with reactant B, which eventually forms our product, C plus D, and here we start with A plus B. Again, I'm using the reaction from here just because it's something that you were familiar with, that we saw. So what's special about this? Okay, a few things. We can still figure out if it's endothermic or exothermic. Since the energy is dropping, that means it's exo. But we have 2 activation energies. We first have the activation energy here of step 1, so kind of E sub A of 1. And then we also have the activation energy of step 2, E sub A of 2. Sometimes you could have 3 steps, and then you would just have, instead of 2 humps, you would have 3 humps. And we'll play around with a lot of energy diagrams like that, but we want to be familiar with these, how to figure out if it's endo or exo. You need to know what an intermediate is, what the rate-determining step is, that the rate law of the overall reaction is the same as the rate-determining step. You need to figure out how to get the overall reaction from the steps. You need to know these 3 terms, unimolecular, bimolecular, termolecular, and you're good to go with mechanisms and collision theory.